Okay, so we're doing the warm-up using our information from yesterday. We want to find the projection of V onto U, and we're given the Cartesian vectors in 2 space, V and U. So if we look back at our formulas from yesterday, I'll just pull that up, lots of tabs open. I am focusing in here. Oh, I just realized that this is frozen on your end. Shh, guys, silence, be calm. Okay, so this looks a little bit kind of crazy right now, but I'm focusing on the Cartesian projection formula up on the top right here. And because we're finding the projection of V onto U, this formula should look exactly the same as it looks up here. So I'm using the one on the very right over here, where it says U dot V over the magnitude of U squared times vector U. So that is what I'm starting out with here. So U dot V over magnitude of U squared times vector U. So different than dot vector U. So what we're going to get from this section right here, the first section, is a scalar, and then we're going to multiply that scalar by our vector. Now the nice thing is that when we're working with Cartesian vectors, when I do the projection, we said a projection is different than the dot product because the dot product gives us out a scalar, but projections actually give us out a direction as well. And when I'm working with Cartesian vectors, when I finish and I finally found the final x component and y component of my Cartesian vector, that thing has both magnitude and direction. So I don't have to actually worry about like calculating for an angle or anything like that. Okay, so I'm going to do U dot V, which means that I'm taking the x component of V and U and adding them with the x components of V and U multiplied. And then I'm going to do magnitude of U squared. So the magnitude of U can be found by doing the x component of U squared plus the y component of U squared, all square rooted. So what ends up happening here is that the squared and square root cancel. And then I've just got times vector U over here. Ryan, zip your lips. Okay, so we're getting -5 and -6 on top, which gives us -11. And then on bottom here, I've got 25. Yeah. So we've got root 34.
Isn't it just 34?
Oh, yeah, sorry. You're totally right. Because the root canceled. So I've got 25 and 9. And then we're just multiplying that simply into our vector, because this is now a scalar that's being multiplied by our vector. Oops, sorry, this should be a square bracket. Ryan, shh, silence. He just keeps talking. What is happening right now? So I've got -55 over 34, and then negative here make positive, so 33 over 34. That's our final vector. Okay, all right. So this contains both magnitude and direction. Any questions for this one? Olivia.
When do we need to know when to look at like which quadrant it's in to figure out if it's negative or positive?
So I'll just slide over to an example from yesterday. Did we have to decide on that yesterday, or was that a couple days ago? I'm trying to remember. I think it was a couple days ago. Trying to remember here. I'll find the sample for you after, and I'll show you. I'm just not remembering the example in my mind right now.
But it's not when we're doing like projections.
No.
Or dot products? Yes.
It is when we're doing dot product. Yeah, I think so. Yeah. Okay. So moving forward with our new material today, we are actually extending our knowledge now from flat 2D space into 3D space, which is often abbreviated as 3 space. So we write them using ordered 3 tuples, A, B, C, or X, Y, Z. corresponding to our x, y, z space. So this can be somewhat maybe difficult to draw on a 2D surface, but you have to imagine that this line right here is actually kind of like projecting outward. So we can kind of see this in 3D space. They all meet each other at a right angle, just like the x and y axis meet each other at a right angle. It looks a little bit different because it's kind of like it's kind of skewed because we're looking at it on a 2D surface. But this is how our axes end up changing when we're in 3 space. So this is actually x, y, and this is the z axis because we're Canadian. Okay, and these are all what I've drawn for you here. These are all the positive x, y, and z axes. So the negative ones, we'll just kind of pencil those in with a dotted line here. So this will be like the negative y-axis right here. This will be the negative z-axis. Okay, and then kind of going backwards into space here, this is the negative x-axis right here. Okay, so you have to kind of imagine this like the YZ one is like our usual XY axis, and then our X is kind of like projecting outward. So the rule usually is if you take your right hand and you kind of curl your hands toward yourself, this is the Z axis, your thumb pointing up, this is your X axis, and your Y is like your arm is like your Y axis. Okay, Mark? Yeah, so imagine the X is pointing at you. Yeah, yeah. Mark?
Does it matter if we switch X and Y?
For our purposes, you'll want to make sure that you draw it. Like, we all want to be consistent, right? Like, if I go ahead on the Cartesian plane and all of a sudden I switch X and Y, that matters, right? So here it matters too.
So X is always like this?
Yeah.
It's always like that?
Yep.
Wait, X is like, how do you do it?
So imagine, guys, so the Z and Y here are flat, and imagine my pen is the x-axis coming out at you like this. Okay? Okay, so if we take our right arm, curl your fingers back toward you. Okay, this is the x-axis. My hand here is the x-axis. My thumb is the z-axis, and my arm is like the y-axis. So we're stretching it, well, I'm keeping it like as if the Z and Y are flat on the board, right?
Yeah.
So you have to be going in the same direction that I'm going, right? Okay. Yeah. Yeah, exactly.
It's right-hand
Yeah.
rule.
Yeah, that's what it's called. So there we go. Okay, we're gonna do an example. Okay, so if we wanna do a sketch, again, keeping in mind that this is a 2D surface, this can potentially be a little bit challenging. So ladies in the back, are you good? So what we end up actually doing is we kind of create like a box so that we can kind of see what's happening here. So we want to go forward. So this is X, Y, and Z. We want to go forward on the positive x-axis 3. So we'll say, oops, we'll say 1, 2, 3. So this is going to be 3. So this is a component of our box right here. And then I want to go left on the y-axis 2. So let's just say this is -2. So that's the other component of my box there. And then my other part will be up 7. So 1, 2, 3, 4, 5, 6, 7. And that's going to be part of my box. So out of these 3 things, we're going to kind of make a box. So imagine like not a cube, but a rectangular thing here. Sorry, this will be Zainab.
You know how you put the axis to
Yep.
why is it going in the matrix? Why is it in
So that is the positive x-axis.
the opposite side of the dimension?
Yep. So this side over here is the negative x-axis. Yep. Okay, so we're drawing a cube here. Mark's going to use his art skills.
It's actually amazing.
Why isn't art like a prerequisite to calculus?
I try. Does it look like it's coming out at you?
Architecture is like
Thank you, thank you. I'm here every day. Okay, let's draw our vector now. Okay, so guys, remember that our vectors, just like in 2D, our vectors start at 0, 0, and the tip ends at the point where we go up 3, left 2, and up 7. So that's this outer corner of our box here. That is the point 3, -2, 7. So our vector is actually coming in space here. It's coming out toward you, going on the diagonal of that box. So starting at the point 0, 0, 0.
How do we know that it was that direction?
It will always be that outer corner of the box. Yeah. The outmost corner of the box. Or I guess like it depends whether it's in the positive x-axis or negative, but it's going to be like the farthest corner of the box from 0, 0, 0. Yes, Ryan. Okay, so follow the path here. So we're going positive. What can I do this with? Let's do it with pink. We're going positive 3 on the x-axis. I'm going left 2 on the y-axis and up 7 to get to where the tip of my vector is. Does that make sense? So we're finding a path that will take us 3. Yes, it will. Okay? All right, calculate the length or magnitude of our vector. The length or magnitude of our vector, we'll just call it length for now because the vector doesn't have an actual name, is calculated very similarly. Shh, guys. Mark, focus. Okay, it's calculated very similarly to how our 2D vectors are calculated. Olivia, question?
So those pink lines are those are the original ends of that vector.
Those are the x, y, and z components of our vector, of our point that creates our vector. Okay, so in 2D, how do I find the magnitude of a vector? Zainab? Right, I do the root of the x squared plus y squared components of that vector. So any guesses to how we do 3D? Zainab? Yeah, same thing with these, but also we have that z component now, okay? So we're going to take the square root of the sum of all of the squares of each component. Guys, shh, be quiet. If you have a question, ask your question. Someone else might have the same question. So remember here, guys, that if I'm trying to find the distance between two 3D points, I'm doing like, I'm subtracting the two x components, but because this one starts at 0, 0, it's like I'm doing 3 minus 0, and then -2 minus 0, and then 7 minus 0. That's why we can just do the x, y, and z components here, because the vector actually starts at 0, 0, 0. Zainab?
Wait, so if it was inserting at origin or whatever, like where would you,
Yeah, so you would be doing like x2 minus x1, and then like y2 minus y1, and so on, z2 minus z1. But we always express vectors as if they start at 0, 0. So what you would just have to do first is find the vector, and then you can do it regularly, like how we're doing it here. Yeah, you essentially do x2 minus x1, y2 minus y1, and z2 minus z1. So you're doing it either way, technically. Okay, so you should get root 62 for this. Okay. Can I move forward? Any questions? We're good? Okay. Calculate the angle between vector u and vector v. We talked before about how we can kind of use the dot product to help us find the angle when these two vectors are arranged tail to tail. So I'm going to use the idea of u dot v. And we know that geometrically, this is where we kind of use the geometric formula to help us with these Cartesian vectors. This is my geometric formula for the dot product. So we're finding the angle. So we're going to divide out their magnitudes. and then we'll do the cos inverse. Okay, so we're going to dot, and I think you guys can probably extend your idea of the dot product. So usually what we would do in 2D space is we would do the x components being multiplied, and we would add the y components being multiplied. Now because I'm in 3 space, I also have to add the z components being multiplied. Okay, and then maybe off to the side I'll do magnitude of u and v, and then we'll just plug them in. So magnitude of u is going to be the square root of 0 squared plus -1 squared plus -4 squared. And then same idea for v. Okay, so 36, 1, and 4 is 41. Okay, so we're doing root 41 times root 17, and I want to take the cos inverse of this whole thing. You can simplify it first before you take the cos inverse if you want, but yep. Multiply these. So we'll always do that multiplication with the dot product, but sometimes it's slightly different when we're working with geometric vectors. So we're always doing this multiplication when we're given Cartesian vectors like this. Okay? What'd you guys get for theta? Let's round to 1 decimal place.
74.6.
You are correct. Very good.
7.62.
Okay, so guys, it doesn't matter if our vectors are 2D or 3D. Like if we imagine these two vectors being 2D, I can find the angle between them, and then as soon as one of them goes into 3D space, I'm still finding this angle between them. So the angle is still the same whether those two vectors are flat or whether they project out into 3D space, okay? So same kind of idea. Olivia?
So because there's 3 axes,
Yep.
angles.
So again, like if I'm finding the two vectors and they're flat, if I have one that's going out into 3D space, I'm still just finding this angle between those two vectors, right? So any two vectors, like this is in 3D space right now, like holding these two pens, right? It's in 3D space, it's not flat. I'm finding the angle that's like right in between them. Okay? Zainab?
Sorry, but what is this calculate the angle between like the
Yep.
Do you know what to use, geometric or Cartesian?
So we always use this geometric formula to help us find the angle between vectors. Yeah. Yeah, because it's the only one that has the theta in it. So if you're not sure, just look for the one that has the actual angle that you can solve for in it. Yeah. Ryan? Cos of the second. So the second equation is just me dividing the magnitudes. It's the same equation. Sorry, what? Yeah. So I'm just showing you, that's the geometric dot product, and then I'm dividing out the magnitudes to show you how to solve for cos theta. Olivia?
So when we're looking at the example we drew out,
Yep.
if we're looking for the angle, would it be between that diagonal one we drew and then one of the axes?
It will be between where the other vector is. Okay, that's just one single vector. This is two vectors, right? Yeah. Okay. Calculate the magnitude of the projection of two vectors in 3 space. Okay, so let's look back at our formulas here quickly. This is Cartesian. Oh, what happened? Where did they go? Oh, I scrolled up. That was my fault. Okay, Cartesian. I'm looking at this guy down here. The projection of v onto u is the dot product divided by the magnitude of the vector that's being projected on, and we just want to take the absolute value of that because we don't When we take magnitude of the projection, I'm not interested in whether it's in the same direction or opposite direction. I'm just interested in that magnitude component. Okay? So we are finding the projection of u onto v. So this one is slightly different than, than our other one. Because this is v onto u. So instead of dividing by the magnitude of u, we will divide by the magnitude of v, because v is the vector that's being projected on. Okay? So we are finding projection of u onto v, which means that, and I want to find the magnitude of that. So I want to take the absolute value of the whole thing, and I'm going to do u dot v over magnitude of v. That's how we're going to find it with Cartesian vectors. Okay, so u dot v, same deal. We're going to take the x components, add them with the multiple of the y components, and the multiple of the z components. And then magnitude of v is the square root of each of these guys squared, each component. And then if this happens to be negative, I'll just want to take the absolute value of that whole thing. I want no negative answers when we're talking about magnitude. Okay, so here I think we end up with all positives anyways. We just get 9 over root 29. So that's the magnitude of our projection. Oops.
Do we have to rationalize?
I won't be super picky about it. You can. The textbook might. I'm not sure.
I think we should. I'll take that as a big no. If I lost one of
It's
my
just
guys,
9 root 29 over
that's
29.
pretty intense. That's a big difference.
So,
There's a whole nother twist for it.
Ryan? Okay, guys, listen. Ryan's asking a question. Shh.
Why, depending on which way you project it, what goes where?
So, I mean, this is in 3 space, but if we imagine 2 vectors in 2 space, if this is u and this is v, I'm interested in the shadow that u casts onto v if I'm doing the projection of u onto v. If I'm doing a v onto u, I'm interested in the shadow that gets cast in the direction of u, from v. So in this case right here, if I'm doing projection of u onto v, my light's coming from up here and it's creating a shadow down here onto v. Okay? If it was the projection of v onto u, my light would be coming from down here. Again, it's perpendicular to vector u, and it would be casting its shadow like down here at a right angle over here. Okay? So 2 different directions totally. Yep.
Compared to our warm-up, why do we use like this formula to this one?
This is magnitude, whereas our warm-up was just the projection itself. So in this one, we're not interested in direction.
So this one we're just like in the magnitude of the projection? Like
Right.
The warm-up, it was just,
Projection itself.
oh, like the location of like the project?
So the projection is a vector always. So it will tell us magnitude and direction. When I'm finding the magnitude of the projection, I'm not interested in the direction component of that, just essentially the length of that projection.
So this would just be like the length of it? How
Right.
Like the length plus like, oh, because it's negative, we got a negative initial like axis on it, yes. So it told us like where it was.
So when we do, like you'll notice in the warm-up, when we do direction here, so this is the magnitude component. This is what we're getting in our question below. We're just getting this component, and then this part gives me the direction of u as well. Yeah. Or actually, you know what? I shouldn't say that because this is just like the scalar multiple of this. But this component over here does give us the direction component. That's why we need the x and y to kind of tell us where the vector is headed. Does that make sense?
Yeah, like, but.
Okay, but we're not doing, so part of this, we're not getting the full, like, single magnitude of the projection because this is the magnitude of u squared. But if I separated these out, you'll notice that we get magnitude of u, and I'm just going to kind of show you over here. This is magnitude of u. This is simply the direction of u. This is u hat, okay, the single unit vector in the direction of u. So when we find the magnitude of a projection, we're just interested in this part of the formula. Better? Okay. Okay. All right. We have a parallelogram EF, GH. It has points E, F, and H that are listed here for you. We are tasked to find point G. So while we realize that this actually is 3-space and it could be kind of jutting out, we're just going to draw ourselves a 2D picture so that we can kind of get the idea. So no matter where this parallelogram is, like if we imagine this paper, the paper can be flat for sure, and we can draw it 2D. This is a parallelogram, right? It's also a rectangle. But I can also take this rectangle and I can put it out into 3D space. Does it really change the fact that it's a parallelogram? Not really. So we can kind of just draw a picture here for reference, as if it's like a 2D surface. So we're going to have E, F, and then G, H. And I think the picture just kind of helps us visualize what's happening here. It's not imperative that we have a picture, but yeah, it can be helpful. So we'll call this EF, G, H. Okay, so in order to find point G, we're actually going to kind of use the fact that somewhere over, we're not sure where it's orientated, but somewhere we have the origin over here, right? Because we always express all of our vectors as if they come from the origin. So it might be helpful for us to have that origin component so that we can, right now these are points, they're not vectors. So if I want to turn them into vectors, I need like OE and OF and OH and OG. So let's kind of think about this. If I take the vector from the origin to vector H, that is the vector OH, right? So we can actually express it as like our vector OH. We can actually now express it as a vector, like so. Okay? Right now, H is just a point. It's not a vector. So we're kind of turning it into a vector, starting at the origin and going over to vector H. I could figure out what G is if I can figure out what OG is. So that's my goal. This is kind of like the resultant. This is going to be vector OG. And the component that I would need to add to OH in order to get OG, again, tip to tail, this is kind of the idea, is HG, right? I'd have to go from H to G. So do you guys agree if I say that OH plus HG is equal to OG? Right? We kind of cut out this middle part right here. Does that make sense? Okay. So can I find HG and OH? That's the question. Well, I can't find HG because I don't know what G is. But I can find OH. OH we just wrote above. OH is -2, or -1, -2, -3. HG, perhaps we could use an equivalent vector, EF. Yes. So HG is actually equivalent to the vector EF, so maybe we can use the vector EF to help us. That will still be equal to the vector OG. Ryan, question?
I don't understand what you got.
So right now, E, F, and H, as they're stated to you in the question, are just points. They're not vectors. So if I want to turn them into vectors, I will represent them as the vectors that are going from 0, 0, 0, or the origin, and then the tip is ending at each of those points.
No, like I know that, but like how you get -1, -2.
Well, if I'm trying to find a vector here, this is saying it's starting at the origin and ending at H. I'm doing like x2 minus x1, which is like -0. So it's like -1 minus 0, -2 minus 0, and -3 minus 0. So that's kind of how we find it. It's like x2 minus x1, y2 minus y1, and z2 minus z1. Okay, maybe it will clarify for you when we find vector EF. Okay, Zainab?
So is always the like vector just
so long as it's starting at the origin. Right? EF is not starting at the origin, right? Okay, so can you guys remind me, how do we find a vector when I have the tail of the vector and the tip of the vector? What do we do? So tip components minus tail components, right? Yes. So we're going to get, what's our E and F here? It'll be, so these are the X tail components, X tail, Y tail, Z tail, and this is the X tip components, Y tip, and Z tip. So I do the tip components minus the tail components. So I'm going to do -4 minus 9, 0 minus 2, and 1 minus -8.
So it doesn't matter which one.
What's that, Olivia? Order does matter. It's tip components minus tail components. Okay, and now how do we add two vectors? What do we do? You don't know? What's that, Mary? Yeah, so I'll add the x's, I'll get -14. I'll add the y's, and I'll add the z's. So if this represents the vector going from 0, 0, 0 to the point G, can somebody tell me what the point G is? Oops.
-14, -4, 6.
Yeah, so point G is just this single point. So this is the vector, again, that goes from the origin to the point G. So we know that the point G is simply -14, -4, and 6. Okay, so in these types of questions, we have to kind of use the origin to help us out so that we can create vectors from those points. Okay? That's what I want. Can I answer any questions before we move forward? Mark, go ahead.
Like if it's a parallelogram, how could E be -8 and then F be like 1 and then H be -2?
So remember, this is,
Twisted.
well, it's not going to be twisted, because if it's twisted, then opposite sides aren't parallel. So I still have to have something like this, but it can be rotated for sure. I'm finding the point G that makes sure that that's all opposite sides parallel and equal, right? But essentially what I have is a shape that's being moved in 3D space, right? It can be like, it can be on an angle like this, right? So we're solving for the point that makes sure that this is a parallelogram. Okay? Here, I'll move up for you. Is that good? Yeah. Okay, anything else that I can clarify here? Okay. Yeah, so these are equal vectors, parallel and opposite. Yeah, or parallel and equal, sorry. Can I scroll, Mark? Are you okay? Okay. Okay, do we need a 2-minute break?
No. Let's go.
No? Okay.
We've got our topics.
All right, so we are finding a vector. We're almost done, guys, so if you can just focus in here for the last couple minutes. We're going to find a vector that is what we call orthogonal, which actually just means perpendicular. Okay? So we are tasked with finding some vector that is orthogonal to the vector 3, 4, 5. Okay, so the vector 3, 4, 5, it's somewhere out in space, right? Something like this. Now, orthogonal meaning perpendicular means I just have to find one vector that's perpendicular to this. So we're just holding our pen out. Now imagine, so I have to have a vector that's perpendicular. It can be literally anywhere on this line. It can even be this way. It can go this way. It just has to form an angle of 90 degrees. So it could literally be like anywhere along here, as long as when I calculate that angle, it's 90. So there's actually like infinite vectors that are orthogonal to this one. Does that make sense? Because there's any vector that I could kind of put on this pen that I have here, and it will still be at a 90 degrees. So what do we know about the dot product when we have two perpendicular vectors? Okay, so here's the idea. If I call this A and I call this B, I know that because these are perpendicular, that their dot product should equal 0. That's the rule with perpendicular vectors. So when I do the dot product between A and B, I want to take the x components and multiply them. So this one will be 3 times x. I want to take the y components and multiply them, and then the z components and add those all together. So this is what I have. And I know that that dot product must be equal to 0. Okay, so because there are infinite answers to this, there's not only one right answer. Like we could all probably find a unique answer and have no overlap here. So we are just going to actually arbitrarily choose 2 of the values, and we solve for the third value that makes that true. Okay? Because again, there's infinite. So I can find one that has the points, let's say maybe 2 and 1 for the x and y, and I just have to simply solve for the z that makes the dot product equal to 0. So again, infinite answers here. So let's suppose we let x equal 2 and we let y equal 1. And then all we really need to do is just solve for the z that makes that dot product 0.
Is it possible for one of them to be 0?
Yeah, for sure.
They both be 0?
Yeah,
Actually, maybe 2 of them don't.
potentially.
No, but then
So we got 6 and 4.
What if all 3 of them were 0?
That is not possible. Because again, yeah, you don't want all of them to be 0 because that's the 0 vector, right?
Okay.
So sometimes this isn't going to work if both of these are 0, because then, yeah, I guess actually 2 components can't be 0. 1 component can be 0. But if I have 2 components being 0, that means the third component must be 0, and then you're using the 0 vector. So that doesn't work. Yeah. Yeah, so you choose 2 of them and you find the third. Any 2. So we could all find different answers if we wanted to. Sorry, I shouldn't have put the vector symbol on that. Okay, so z is equal to -2. So a vector that is orthogonal to vector b is the vector 2, 1, -2. You can do a little check here. If you want to check the dot product one more time, you would check that the dot product is equal to 0. So again, you don't have to because we kind of just used it to find this, but we could do a little check and just ensure that 2 times 3 plus 4 times 1 plus 5 times -2 does in fact equal 0. And then we get, shh, guys, my goodness. We get 10 minus 10 equals 0, which gives us true statement. So the dot product, yes, the dot product is 0, meaning these are orthogonal. Ryan? For 2 of them, and then you find the third. Although don't choose 2 of them to be 0. You can choose 1 of them to be 0, but not both.
So I could have used like 50 and 100.
Yes. Okay, this one worked out nicely. I kind of chose numbers that made this work out nice so that z was a whole number, but you could get z as a fraction for sure, and that would still be true. Okay, so we are going to, actually let me just stop this here.